Lesson 18 on binomial distributions. So it turns out that the Monty Hall problem that we talked about is deeply involved with these binomial distributions. Let's take a look here. So let's say that x, this random variable, represents the number of wins among the 18 rounds played under the switching strategy. Then x has as its distribution a binomial distribution, BIN, where the number of rounds or trials is 18, and the success probability per trial, P, is 2/3. 2/3 is the probability that you win the car under the switching strategy for any given round. Okay, so this is a distribution, all right? So x is a random variable that can take on a value between 0 and 18. If you play 18 rounds of this game, then you can win the car between 0 times and 18 times. X can take on various values between 0 and 18. Now, the binomial distribution involves these possible values of x and their corresponding probabilities. Now, there's almost no chance that you win the car no times or 1 time or 2 times, for example. The most likely number of wins is, look at this, 12 out of 18. That's one reason why I chose 18 rounds. 2/3 of 18 is 12. It turns out that this is the mean for this distribution. Now, the probability that you win the car 12 times out of 18 under the switching strategy is about 20%, 0.196, and it's the highest probability of all of these. So it's not surprising that 12 is the most likely number because 2/3 is the success probability. 12 is 2/3 of 18. So this is the probability distribution for x, the number of wins out of 18 rounds. It's almost 0 over here. Then it goes up, 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 and it peaks at 12 wins out of 18 rounds, then down, 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 and it's very unlikely that you win the car all the time. Of course, these probabilities add up to 1, give or take rounding error. Now, actually, we saw this in practice, at least I did. In 5 of my statistics classes, 101 pairs or teams of students played this Monty Hall game. They played 18 rounds of this game, and they recorded the number of times that the student contestant won the car out of the 18 times. For each pair, the contestant was one student and Monty Hall was the other student. So, based on the 101 teams, no team saw these numbers of wins for the car, 6 or fewer. Nobody saw 6 or fewer wins in this switching strategy. But as a matter of relative frequency, it went up, 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 up. This time it peaked at 11, but 12 was also pretty high over here. But you saw the highest relative frequencies for basically 11, 12, 13 wins out of 18. Now, as you see, the relative frequencies that I actually observed in my 5 classes, they did not match the theoretical probabilities perfectly, but they were pretty close. They were pretty close. And again, we saw a peak at around 2/3 of the 18 rounds, about 12 or 13. Okay, so we're seeing the binomial probabilities playing out in these relative frequencies, and I can guarantee you that if instead of 101 teams, if I had 1,000 teams or 10,000 teams, then the relative frequencies would have very closely matched the theoretical probabilities over here. Okay, so this is an example of a binomial distribution. What defines a binomial distribution? All right, what is a binomial experiment? First of all, okay, so basically the Monty Hall game that we played and this game we're going to talk about here, they're going to represent binomial experiments, which give rise to binomial distributions. So let's say that I'm playing Yahtzee and I roll a standard 6-sided die 5 times, or equivalently, I roll 5 such dice at the same time. Let's say that we count the number of 4s on the 6 dice. Let x be the number of rolls, or the number of dice, coming up of 4 among the 6 faces. Now this is a binomial experiment, and x, which counts the number of 4s, is a binomial random variable. Now why is this a binomial experiment? Okay, so first of all, and don't worry, you won't be tested on this, but you need to know a binomial experiment when you see it. First of all, we see a fixed number of independent trials. In this case, for the dice, 5 rolls or 5 dice. For Monty Hall, it was 18 rounds for each of the student teams. Each trial results in either a success or a failure. So with the Monty Hall rounds, the contestant either won the car or didn't. For the dice, a success is when a 4 is rolled. A failure is when something else is rolled, like a 5 or a 6, or a 1, 2, or 3. So the idea is that we're counting successes. X is a binomial random variable that counts successes, which would be car wins in Monty Hall or 4s in this dice example over here. In some medical situations, X could count deaths, in which case you may not want to be successful. Number 3, for each trial, there is a fixed probability of success. And we call that fixed probability P. In the case of dice, P, the probability of rolling a 4, is 1/6. The failure probability is the complement. It's 1 minus P, or what we call Q, the failure probability. Q is 1 minus 1/6, or 5/6. Is the probability that a die comes up something other than a 4. In the Monty Hall problem, P is 2/3 and Q is 1/3. Okay, so in both the dice example here and the Monty Hall problem, we're talking about binomial random variables, X, which counts the number of successes from a binomial experiment. Another classic situation is when you're flipping coins. Here is another Rossmann chance applet. Let's say that we take a fair coin, probability of heads is 0.5, and we toss the coin, how about 100 times, like many of you did in the extra credit problem. Okay, let's draw the samples. All right, and this particular student got heads 44 times and tails 56 times. Okay, now let's say that instead of 1 student, we had 1,000 students flipping 100 coins. So 1,000 students doing this extra credit problem. Let's draw the samples. All right, this was the last student. We care really about this relative frequency histogram over here. You can see that it's peaking at about 50 heads out of 100. Now, this is what we're seeing from the simulation where 1,000 students are flipping a coin 100 times, a fair coin 100 times. According to the binomial distribution, the frequency distribution should look something like this in green. And as you can see, it very closely models what we actually saw from our simulation. And guess what? This binomial histogram very much resembles a normal bell curve. And in fact, we're going to investigate that later on. The fact that normal bell curves can sometimes approximate binomial histograms. Okay, so we're going to talk more about binomial experiments and binomial distributions in our next video.